About 12,800 years ago, the climate on this planet broke in a way that nobody can explain. I'm Curtis Holland, and I'm an independent historian who studies ancient history, ancient symbolism, and ancient texts through a scientific and first principles lens. And today, we have to look at an event called the Younger Dryas, what it was, what the data shows, and where the current state of research on this event is at in 2026. The Younger Dryas is a colloquial term for a cold snap, a period of time halfway in between the last glacial maximum and today. The name itself is derived from the Dryas octopetala plant, a plant that prefers cold weather temperatures. In the 1800s, a Swedish researcher was doing research on this particular plant. He noticed in the stratigraphy layers that it occurred rather close to glacial ice. And about 26,000 years ago, this plant was relatively present. And then for a period of time, it goes away. It stops showing up in the areas of Northern Europe as the temperatures continue to warm. Until about 12,000 years ago, where the plant mysteriously shows up again in the stratigraphy layer. And it's there for about 1,300 years of time before again disappearing. The researcher deduced that there must have been some type of cold snap or cold period in this region of the planet that accounted for this plant reappearing in the record. Further research over the course of the last 100 years confirmed that this showed up everywhere, and modern Greenland ice core data verified this trend. You see, this occurs right in the middle of a warming period. If you were to remove the Younger Dryas from the history record, you would see a steady warming curve. From the last glacial maximum to now, you see temperatures around the planet rise into what they are today for the Holocene temperatures. This time period is known as the Bowling Alarad. It was a warming period having to do with where the planet sits in relationship to the sun. You see, this warming was always going to come. The Holocene is part of a regular cycle that this planet goes through every 40,000 years or so. The anomaly is specifically this. Halfway in between that time, roughly again 12,000 years ago, the climate did a full 180. It went back into glacial ice, glacial temperatures. Temperatures around the whole planet dropped precipitously, and over a rapid period of time. Every civilization you've ever heard of, Egypt, Mesopotamia, Greece, Rome, all of our ancient history occurs since this event happened. If you've seen our last video, you would know that the Ice Age world that humans lived on was dramatically different from our own. The environments were different, shorelines were different, there were land masses that are under sea now. Places like the Sahara and the Amazon were more habitable than they are today. The climate itself was rather inhospitable to our modern versions of agriculture and farming. And as the planet was approaching an equilibrium that is more suited to the way we humans live today, it did a full 180 in temperature. That makes the Younger Dryas not just a climate anomaly, but a human story. Because the Younger Dryas is the last major event to occur prior to our modern time period. Now, here's the thing. Everybody agrees that the Younger Dryas happened. The data is obvious. You can't ignore it. The debate comes around what caused this rapid cold snap. Why did it last for 1,300 years, essentially in equilibrium? And then what caused it to revert back to the normal warming period, roughly 10,500 years ago? As we work through this, I'll discuss the data that we have on this. Many of it is uncontested. Some of it is contested at the level of interpretation. As we discuss this data, I'll be clear to emphasize which is which. Now, before we get into the debate about what caused it, we need to first understand what it is we're looking at. So let's start with the temperature signals. That's the basic one. That's the most readily observable in all of our ice core data. Modern Greenland ice core data shows the Younger Dryas beginning about 12,870 years before present. Scientists can read the chemistry of the ice to reconstruct how air was circulating across the northern hemisphere at that time, and the signal of how the air was moving flipped in about 1 to 3 years. That's the entire weather system of the northern hemisphere doing a complete 180 in less time than it takes to finish high school. You see, it typically takes about 50 years for a full temperature drop to occur at a stable rate. And as our technology has improved and the data has become more precise, we are finding that the onset of this Younger Dryas occurred in a shorter time period than we had initially interpreted. The magnitude was severe. In Greenland, annual mean temperatures dropped somewhere between 4 and 10 degrees Celsius. It reached as high as 15 degrees Celsius in certain locations. Across Europe, temperatures dropped anywhere from 3 to 6 degrees Celsius. And in North America, where the Megafauna Extinctions and the Clovis collapse was hit the hardest, about 3 degrees in the eastern and central regions. And all of that occurring in approximately 1 to 3 years. You see, that's what matters. Not how far the temperature dropped, but the rapidity at which it fell. And what resulted from it once those temperatures hit that level. But the temperature drop is only part of the story because while northern hemisphere was cooling, the southern hemisphere was warming. Scientists call this pattern the bipolar seesaw. Essentially, it was the balancing act of the planet. The heat didn't go away, it wasn't dissipated, it just moved. And as the temperatures in the northern latitudes fell, the temperature in the southern hemisphere rose. What moved these temperatures was the ocean. There's a circulation system called the AMOC, the Atlantic Meridional Overturning Circulation. During the Younger Dryas, that conveyor belt shut down and stayed that way for 1,300 years. The warm water stopped reaching the north. As I said, this was a global event. The tropical rain belt, or the intertropical convergence zone, shifted south. Monsoons weakened across the planet. West Africa, Asia, Australia, all of them experiencing less monsoon rainfall. What that means is that the climate system, the tropical rain belt, and ocean circulations all reorganize themselves at the same time, this Younger Dryas boundary window. So now let's take a look at how this affected the surface of the Earth itself, what it changed and how it affected our world as we know it. There is a physical layer you can see in the ground. It's called the black mat, a dark organic rich stratigraphy layer that shows up across dozens of North American sites and sits right at the Younger Dryas boundary. Vance Haynes documented it at roughly 2/3 of the 97 geoarchaeological sites across the continent. At site after site, the last megafauna remains and the last Paleo-Indian artifacts sit directly below it. And nothing sits in the layer above it. What sits in the black mat layer tells a story. There's elevated charcoal, elevated soot, carbon spherules, and all of these are combustion byproducts. What this means is that during this time there were massive continental scale fires. In the Greenland ice cores, the fire signal at the Younger Dryas onset is one of the largest in the last 130,000 years. Woolbach and colleagues, analyzing the charcoal and soot records from over 150 sites across 4 continents, estimated that fires at the Younger Dryas onset consumed roughly 10 million square kilometers, about 9% of the planet's total biomass. To put that in perspective, that's more than was burned during the asteroid impact that killed the dinosaurs. In fairness, though, that asteroid impact pretty much destroyed anything that could have caught on fire anyway. But the point still stands, and debate about what caused these fires is still ongoing. Now, let's talk about, what happened to these animals, these megafaunal species. In North America, more than 35 genera of large mammals went extinct right at this boundary. Over 70% of large-bodied mammals disappeared. Animals like mammoths, mastodons, giant ground sloths, saber-toothed cats, short-faced bears, American horses, American camels, and direwolves. Yes, direwolves are real. They're not just from Game of Thrones. The extinction pulse is global, but North America got hit the hardest. And here's a fact that should stop you cold. Most of these animals have existed all throughout the Pleistocene, just like humans. The same animals that survived the absolute coldest periods on Earth, that survived millions of years of ice sheets a mile thick over northern latitudes, all disappear in the same window. What kills the populations isn't the temperature itself. They'd proven they could handle that repeatedly over millions of years. What kills populations is rapid change. A shift in temperatures and environment so fast that the ecosystem couldn't adapt before the cold and stress arrives. And the Younger Dryas delivered exactly that. A massive temperature gradient arriving in years to decades, hitting a biosphere that had no precedent for change at that speed. And whatever hit the animals affected humans too. Anderson and colleagues found a significant decline in radiocarbon-dated archaeological sites across North America, starting right around 12,900 years ago, that same time period as the start of the Younger Dryas. Fernando Lopez de Pablo and colleagues found the same pattern in Spain, thousands of years of steady population growth, and then a sharp drop at the onset followed by over 2,000 years of stagnations. Similar downturns show up in Turkey, South America, and the Near East at that same time period. Now, This is what geneticists call a DNA bottleneck. Multiple streams of DNA narrow, and only a few continue into our species today. That signal is there at the Younger Dryas boundary, and it shows up all over the planet. The Clovis Technocomplex, the distinctive fluid stone tool tradition that had spread across North America, disappears from the record at this boundary. Bayesian analysis suggests a gap of several hundred years across parts of the American Southwest, where there's essentially no evidence of human activity at all. Not different tools, not a cultural shift, just silence. And there's one more set of signals worth paying attention to. In the Greenland ice core data, there's an unusual spike in platinum right at the Younger Dryas boundary. Platinum is rare on the Earth's surface, but it is relatively common in extraterrestrial material. That anomaly has been independently replicated at 50 sites across multiple continents. And in 2024, Moore and colleagues reported shock-fractured quartz at 3 sites in the eastern United States. Quartz that cracked so violently that molten glass got injected into the fractures. To do that, you need pressures and temperatures that only a handful of processes can produce. Nuclear detonations, volcanic eruptions, or cosmic impacts. Now, the interpretation of these signals is actively being debated in science today. But the signals themselves are there, they're replicated, and they require explanations that involve extraordinary heat and pressure. So let's talk about these hypotheses. Now, everything I'm going to talk to you about here exists in peer-reviewed literature. Each one has real evidence and real proponents who actively argue for these ideas today. And each one has factors that it can handle and address cleanly, and each one has factors that it struggles with. The first hypothesis I want to talk to you about is probably the main one, which is the Meltwater Hypothesis. At the end of the last ice age, a massive proglacial lake, Glacial Lake Agassiz, sat along the southern edge of the retreating ice sheet in North America, basically right over Canada. The hypothesis, originally proposed by Broecker and colleagues in 1989, is that this lake catastrophically drained into the North Atlantic. Essentially, the massive pulse of fresh water was injected into deep water formation zones and shut down the AMOC. Now, this does a really good job of explaining the climate response. The bipolar seesaw, the change in temperate zones, and the change in tropical rainfall zones, all of that fits with an AMOC shutdown due to meltwater. And it also explains how this could last for centuries. It takes centuries for the AMOC to start back up once it shuts down. But the main issue here is that the sedimentary evidence for a massive Agassiz drainage has not been consistently found. And there's a useful comparison. About 8,200 years ago, a separate, well-documented Agassiz drainage event produced a real, but much smaller climate permutation, which raises the question of whether a meltwater pulse alone is powerful enough to do what the Younger Dryas did. And the meltwater doesn't address the megafaunal extinction, the carbon mat layer, and the shock quartz and platinum anomalies that we see in the data. Now, the second major candidate is volcanic. About 12,880 years ago, a volcano called the Lacher See erupted in what is now Germany, one of the largest eruptions in late Pleistocene Europe. A 2026 modeling paper by Vetteretti and colleagues in the Science Advances showed that under glacial background conditions, a volcanic eruption could theoretically push the AMOC into a collapsed state. So the physics works in a modeling system. But here's the problem: scale. Lacher See ejected roughly 6 cubic kilometers of magma. The Minoan eruption of Santorini, which destroyed one of the most advanced civilizations in the Bronze Age Mediterranean, ejected somewhere between 28 and 41 cubic kilometers. That's 5 to 7 times larger than the Lacher See. And the Santorini eruption didn't trigger a 1,300-year ice age. It didn't collapse the AMOC. It didn't trigger massive megafaunal extinctions across the entirety of the northern hemisphere. None of this means volcanoes played no role. Maybe Lacher See was one stressor among several, but the scale doesn't match as a standalone trigger. Now, here's the thing: in modern science, the volcanic and meltwater implications address the cooling, but they don't explain the other half of the data, the megafaunal extinctions, human population bottlenecks, or fire signatures that we see in sediment data and ice core data. And to do that, these theories typically turn to 2 main explanations: The first is the Overkill hypothesis, proposed by Paul Martin in the 1960s. Paleo-ending hunting pressure drove North American megafauna to extinction. The second is anthropogenic burning. Humans set landscape fires that spiraled out of control and destroyed megafauna habitat. Now, both of these have data supporting them. There were definitely large hunting sites for Paleo-Indians to get food. There were also attempts at landscape forming through fires set by these same Paleo-Indians in order to help control the land. But both of them fail under the same problem: scale. The Clovis culture lasted roughly 300 years. Estimated Paleo-Indian populations were small, and they were highly mobile bands spread thinly across an entire continent. The megafauna numbered in the tens of millions. Multiple independent researchers have all pointed out that reconciling the actual population evidence with a continent-wide extinction pressure is extremely difficult. And the anthropogenic burning and hunting asks us to believe that a small, sparse population of Paleo-Indians systemically hunted megafaunal to extinction while simultaneously burning the entirety of the North American continent on a landscape that was cold, wet, and partially glaciated. The third candidate is by far the most controversial: the Younger Dryas impact hypothesis, the YDIH, originally proposed by Firestone et al. In a 2007 PNAS paper. The hypothesis is that a fragmented comet or asteroid impacted or airburst over North America around 12,000 years ago. The energy release would have destabilized the ice sheet, triggered continental-scale wildfires, injected dust and soot into the atmosphere, and disrupted the AMOC through meltwater release. Of all the candidates, the YDIH does the best job of explaining the causal factor that can create all of the effects we see simultaneously: the platinum anomaly, the melt glass reported across 50-plus sites, the shock-fractured quartz. But this hypothesis has real holes, and it's important to hold all of these ideas to the same standard. The biggest problem is straightforward. There's no confirmed impact crater of the right age. Proponents argue that the primary impact zone would have been in the Laurentide ice sheet, an ice sheet that was about 2 miles thick at its peak over northern Canada. And that 2 miles of ice has since melted, which would have left no preserved crater. While that is physically possible, it is an argument from absence. And arguments from absence are some of the weakest arguments you can make in a scientific field. Some of the nanodiamond identifications from early versions of this hypothesis have been disputed. Some of the dating carries large error bars. And the hypothesis itself has shifted over time, from a single large comet to a fragmented airburst to ice sheet impacts. Each version addresses the criticisms of the last, but the hypothesis that accommodates every critique by adjusting its parameters is harder to falsify. And harder to falsify means harder to trust, even if that hypothesis turns out to be correct. In 2011, a paper titled "The Younger Dryas Impact Hypothesis, a Requiem," essentially declared the hypothesis dead. And then again, in 2023, many of the same authors came back with an even larger paper, a comprehensive refutation of the Younger Dryas impact hypothesis, a paper that was 96,000 words and essentially a manifesto designed to close the conversation permanently. Since then, the platinum anomaly has been replicated at over 50 sites across multiple continents. Shock-fractured quartz has been documented at multiple boundary areas. The biomass burning evidence has expanded to over 150 sediment records across 4 continents. Now, that alone doesn't mean the YDIH hypothesis is correct. It means that the earlier attempts to close the conversation was premature. So that's where the literature sits in 2026. Multiple candidate triggers, each handling some parts of the hypothesis cleanly and other parts not so cleanly. And one thing every serious model agrees on, whatever happened, it wasn't just one thing. The Earth was doing multiple things at once. The debate is about which factor was the primary cause. This isn't settled science. This is science in progress. And that's worth knowing because a lot of what you might read or see online tries to frame itself as this has been decided one way or the other. It hasn't. So that's where we are. The Younger Dryas happened. We know what the planet did, but we don't fully know why it started, and we don't fully know why it ended. What we do know is that this is the last great climate event before everything we recognize as the modern world begins. But here's the thing I want to leave you with. People get caught up in the how. How did it start? What caused it? Why did it happen? Which candidate is right? And indeed, those are important scientific questions to ask. But the question that actually matters is simpler. Did it matter? And the answer to that question really isn't debatable. Whatever this was, whatever caused it, the people living through it experienced a climate reversal that crashed winter temperatures, killed off the largest animals on their continent, and disrupted human populations for over 1,000 years. And it is entirely illogical to look at an event of that magnitude and assume that humans came out the other side entirely unchanged. Because in less than 1,500 years after this event ends, in southeastern Turkey, people start quarrying multi-ton limestone pillars and setting them up in circles. No clean explanation as to who built it. No clean explanation as to why. It predates agriculture. It predates pottery. It predates writing by thousands of years. The question isn't whether it's connected to what we just talked about. The question is, how? I'm Curtis Holland, and I'll see you next time.